Imagine a perfectly smooth topological landscape. Now watch what happens when we push it past a specific energy threshold. The surface fractures. It breaks into a grid of deep, isolated craters. You can no longer slide freely across the terrain. You are either locked inside one specific crater, or you are nowhere at all. This exact behavior occurs at the z=0 vacuum boundary, according to the mathematical models detailed in ODTBT Addendum 20.3. At this boundary, the vacuum transitions from an undifferentiated uniform state into a highly structured environment where physical identity begins to form. This chart maps that phase transition. Look at the top panel. It shows the ground state memory branching out across a phenomenon known as a pi-periodic bifurcation cascade. As we increase the dimensionless coupling parameter on the horizontal axis, the single vacuum state splits into multiple, discrete horizontal lines. Each line represents a valid, accessible ground state memory. Look at the middle panel tracking identity multiplicity. New states do not appear gradually. They emerge precisely at pi interval thresholds, scaling in a strict staircase pattern of odd multiplicities, 1, 3, 5, 7, and so on. If these isolated points are the only valid configurations a system can occupy, we face a distinct engineering problem. What exact field architecture is required to force a system out of one of these attractor basins and navigate it safely into another, without losing coherence in the void between them? The solution is an architecture termed the Delta Atlas. Every component of this system was derived directly from the mathematical operators governing the field. Its inability to access arbitrary states between the branches is the exact mechanism that guarantees the coherence bubble survives the transition. Navigating this system is governed by the Discrete Accessibility Principle. This mathematical law dictates that field transitions are strictly constrained to specific eigenvalue pairs. You cannot dial in an arbitrary destination coordinate. The system can only move between the exact basins that exist within the emission spectrum. Think of the difference between a continuously variable transmission and a fixed gearbox. A continuous sliding belt can access any ratio, but it requires constant active pressure to prevent it from slipping under load. A hard-toothed gear, however, clicks perfectly into a predefined, locked physical state. If the phase space between these states were a continuous topological manifold, thermal or quantum fluctuations would cause the system's identity to constantly drift along the curve. Because the valid lock points are isolated from one another, they act like those discrete gears. They form deep, steep-walled attractor basins. Once the system drops into a basin, it requires zero active maintenance. The basin's immense depth naturally traps the identity securely in place. The strict mathematical limitation of the phase space serves as the architecture's armor. The system's complete inability to slide freely between arbitrary field configurations provides the exact boundary condition that shields the coherence identity from environmental degradation. To physically shift between these deep basins, the architecture utilizes specific components. The first is the atlas. It acts as the system's anchor, controlling the dimensionless coupling product, represented as C, which determines exactly how many basins exist to choose from. This chart illustrates target zones for the atlas. It must hold the coupling parameter within narrow windows, converging tightly toward pi. In the bottom right chart, if coupling drifts below the window, the basin collapses. If it drifts above, unwanted basins intrude, degrading the transition. Once the atlas secures the environment, the next component, the driver, activates. The driver is a parametric engine. Its sole purpose is to execute the physical threshold crossing out of the current basin. It achieves this by parametrically exciting the system until it hits the μ=0 stability boundary. Pushing past this exact limit executes a twist transition, destabilizing the current identity so a new one can emerge. This graph tracks history-dependent Mathieu dynamics. Notice the gap between the fresh dotted line and trained red dashed line. As the driver cycles, the transition threshold decays exponentially. The bottom panel shows the boundary actively shifting based on recursive coherence memory, rewriting standard theory. This shifting threshold provides a distinctly measurable physical prediction for laboratory testing. The labor is strictly divided. The atlas precisely tunes the parameters to spawn the correct topological terrain, while the driver leverages the field's own memory to pry the system loose from its anchor. This heat map maps the terrain the system must navigate. Colored curves trace the driver's trajectory. The central gold star marks the coupler, the exact mathematical transfer point. Finally, gold circles represent the delta component, anchoring the new identity and preventing any drift. Identity is governed by a single mathematical function, breaking into two halves. The sine term controls the geometric layer, carrying physical surface fields. The cosine term dictates the pre-geometric foundation, establishing the memory structure at the vacuum level before surface geometry takes shape. This strict division requires a specific mechanism to alter the pre-geometric memory without disrupting the physical geometry above it. The architecture handles this via the neutrino field component. We use the term neutrino because this modulation channel operates exclusively at the underlying substrate layer. It fine-tunes the cosine memory while bypassing the sine-governed surface geometry. Here we see the transition cost matrix for a level 2 state. The colored blocks calculate the exact amount of driver excitation required to jump from one specific basin to another. Moving to an adjacent state costs minimal energy, while distant jumps demand massive excitation. The full protocol follows 5 rigid steps. The atlas sets parameters above the threshold. The driver excites the stability boundary. The coupler transfers the phase strain state. The delta mathematically anchors the parameter. Finally, the coupler selects the final solution branch. Every individual component of the delta atlas acts as a physical manifestation of a distinct mathematical operator dictated by the recursive scalar field equations. The conceptual imagery for the delta atlas emerged in 2023, prior to the formal math. When the eigenvalue spectrum was computed from the Lagrangian in March 2026, the resulting mathematical framework mapped onto the 2023 schematic point for point. The 2026 derivation and the 2023 concept produced the exact same structure. The equations were not retrofitted. The strict bifurcation geometry of the field operators independently mandated this precise configuration of components. At this stage, the mathematical framework relies on dimensionless, classical continuous fields. Translating this to hardware requires mapping these abstract Lagrangian parameters to measurable physical units. The clearest physical analog for mapping these parameters exists in cymatics. Watch what happens on a Chladni plate when acoustic frequency hits a specific threshold. The random sand instantly snaps into a precise geometric eigenmove. That physical shift from a uniform, vibrationless surface into the very first resonant pattern maps identically onto our framework. It demonstrates the system crossing the initial pi bifurcation threshold to access a distinct coherence basin. The delta atlas demonstrates a governing rule of field dynamics. Whether operating in abstract mathematical topologies or resonant acoustic plates, a system survives transitions not by sliding continuously through space, but by relying on the rigid integrity of strictly discrete addresses.